Welcome back, everybody, and my name is Jun Wan. Now we are going through the final part of Module 2 RNAseq analysis, and we are showing the result of differential expression. Here is a standard output format after differential analysis from the C3B core, and I believe it's pretty similar to what the bioinformatics core as well. The output is one Excel file. From this one, you can see many informations already being included in the file. The first column is a gene symbol, and from column B to H is something associated with this gene, like a location, chromosome location, and the star end for each exon, and also the total length. And if you are not interested in that part, you may just ignore those parts. However, the columns from I to L are very important. It shows you the result. The yellow highlighted part is a photo change in log2 scale, which means you can observe either positive or negative value. And here we compare knockout versus control. In other words, if you observe negative value, which means the gene expression in knockout is less than the gene expression in control. If you observe the positive value, which means the gene is activated after knockout compared to control. The next column shows the average gene expression across these 6 samples here, and which may give you some hint whether the gene is higher expressed or a little bit lower expressed in the experiment. Column K shows the p-value for each gene comparison, and it will give you whether it's a significant difference or not between comparison knockout versus control in this case. However, column A shows FDR after multiple test correction. And you may already heard many times about multiple test correction, but why we need that, I will show you in next slides. So in the next following columns, we show the raw counts in blue for each samples. The columns in green show count per million or RPKM in log2 scale. When you have the whole data set of gene expression, next step you have to find the reasonable cutoffs to identify differentially expressed genes. Sometimes people ask me a question, can we use a p-value to identify significantly differentially expressed gene? Unfortunately, the answer is no. The reason is we are testing not only single individual genes, but also over 10,000 expressed genes. In other words, we perform over 10,000 hypothesis tests simultaneously. So if we use a standard p-value cutoff like 0.05, normally people use, then we expect 500 genes to be deemed significant by chance. So that's the reason why we need to do multiple test correction to control overall type 1 error. One common method people use for multiple test correction is to use a false discovery rate adjustment. That's also the way we did in our analysis. Another cutoff people may think about is the photo change of gene expression. And sometimes if you think the gene should undergo very significant change in terms of gene expression difference, then we may select a reasonable photo change cutoff. This is a volcano plot. You may have seen many times from other publications. I used one example, most recently published by iScience. And we compare two conditions, PMT5 knockdown versus wild type. And this axis of the volcano plot is a photo change in log2 scale. There is a positive means the gene expression is higher in PMT5 knockdown than wild type. Negative is the other way. And the y-axis represents the statistical significance in terms of FDR-adjusted p-value, but in minus log 10 scale, which means the high value is a smaller FDR-adjusted p-value, represent more significance. After we choose a reasonable cutoff, like in this way, we choose FDR less than 0.01 and the photo change less than something around 0.5, then we may get the number of differential expressions, either upregulated after PMT5 knockdown or downregulated after the PMT5 knockdown. And there are two different conditions here. One is irradiation, the other one without radiation. In this module, we tried our best to explain RNAseq data analysis in details, step by step. And we also have to remind everybody and also ourselves when we interpret the result. The first, we should keep in mind what's the normalization method we used in the data analysis when we compare different samples. And the second is what's the statistical model or computational model we used in our differential analysis. The last one, of course, is the cutoff we choose. Sometimes you may think the cutoff choosing is kind of arbitrary. It may or may not, and also depend on your expectation and the experimental design. After you understand this, you will not be surprised when you compare the gene differential expression list from different datasets, even based on same experiment design. Because people may use the different normalization method or use the different statistical model or different cutoff. So in other words, if you really want to compare two datasets or even one dataset but analyzed from different groups, you may have to think about all these factors we mentioned here. Thank you, everybody. Bye-bye.